Hello and welcome to this quick take video on floating point design with Vivado HLS. In this short video, we'll review the support provided for floating point design by Vivado HLS. This includes explaining how basic arithmetic and math operations are synthesized, and explaining the differences in implementation between operations which are synthesized to RTL and those which are implemented as Xilinx logic cores. We'll then review a design example showing how floating point types are synthesized. Finally, we'll review some additional resources which are available to help you successfully create floating point designs. First, let's review the synthesis process. This example C code uses the C float type. Notice this example has some standard arithmetic operations, multiply, add, subtract, and it has some math operations, sine, cos, and the square root functions. When the code is synthesized, it results in a number of operators which can be represented in hardware, multipliers, adders, sine and cos blocks. During synthesis, some floating point operations will be implemented using a Xilinx logic core, and other operations will be implemented as RTL code. Let's quickly review how the various operations and functions are synthesized. During the high-level synthesis process, the basic arithmetic operations are all implemented using Xilinx logic cores. These are the same cores which users can instantiate today in their RTL code and are fully documented. Both single and double precision types are supported. In addition, each of these operations can be targeted to a specific implementation of these logic cores using the Vivado HLS optimization directives. For example, a multiplication can be implemented using no DSP48s or in a version where the maximum number of DSP48s is used. For math functions, the following single precision functions are supported. Single precision functions are recognized by the suffix f after their name. These functions are synthesized as 32-bit operations. Some of these functions, such as the exponent function, are implemented with a Xilinx logic core, and the results produced by RTL simulation are exactly the same as those obtained in a C simulation over the entire range. Other functions, for example the cos function, are implemented as RTL. For these functions, there may be a difference between the simulation result in C and the RTL. This difference is shown here in units of least precision. A value of 1 means the RTL implementation may differ from the C result by the least significant bit. A value of 2 means it may differ, worst case, by the two most least significant bits. This is the worst case difference over the entire range of operation and is typically a small percentage of the actual C value. For those new to floating point design, these differences in results may seem strange. However, some degree of difference is typical in floating point design, and this is something we'll discuss after the design example. In addition, double precision functions are also supported for synthesis. Double precision functions are implemented as 64-bit operations. Again, some of the functions are implemented with Xilinx logic cores, and some are implemented as RTL code. Here we can see a complete list of all the supported functions. Again, we can see the sine, cos and tan functions. If a math function is not listed in these tables, it is not supported for synthesis. Any attempt to synthesize the design with an unsupported function will result in an error. This list of supported functions is also provided in the Vivado HLS user guide. Now, let's look at a design example. Here we have a Vivado HLS project. If we open the source code, we can see that this is the example we saw earlier. The data type here, data T, is defined in the header file. We can open the header file by holding down the control key and selecting it. In here, we can see the math.h library is used and the data type is defined as a float type. To synthesize this design, we simply press the synthesis button. When synthesis completes, the report opens automatically. Here we can see the number of clock cycles it takes to complete the design. We can also review the area resources. If we look at the details of the area, we can see it's using a floating point, add sub, and multiply units. Here we can see the HDL files. If we open up, for example, the Verilog files, we can see this entire floating point design has been implemented in RTL. If we are happy with these results, We can package this design as IP for use in other tools in the Xilinx design flow. Here we can package for the Vivado IP catalog and simply include this block in the rest of our RTL design project in Vivado, or similarly package it for use in System Generator for DSP or to Xilinx Platform Studio in P-Core format. As you can see, unlike the very complex RTL code which users designing with RTL must write, creating floating point designs is relatively easy and fast in Vivado HLS. For designers who are new to floating point design, or for designers who have only ever used logic cores in the past, there are some challenges to be aware of. The Vivado application note 599 covers all of the potential challenges. It provides a detailed introduction to performing floating point design with C and walks you through each of the challenges with detailed explanations. For example, we have already mentioned in this short video of the differences between some of the C implementations and RTL implementations. Minor differences are often a fact of life when doing floating point design, even when the design is only done in C. Refer to the great example in this application note. Sum 0.1 10 times and you'll get a result which is not exactly 1. Multiply 0.1 by 10 and you'll get a slightly different result. Use double types to perform the same multiplication and you'll get an even different result. These minor differences are part of the challenges when working with floating point types. There's always some trade-off of accuracy versus truncation. More details on how to minimize these differences are discussed in the quick take video using Vivado HLS software libraries in your C, C++ or System C code. In order to have a productive design methodology, the C test bench should compare the results with the expected results. An exact one-to-one comparison will rarely work. As another example, it's important to be aware of the differences between single precision and double precision functions. In the following C code example, variable var f1 is used as the input to a square root function and the output is assigned to variable var f2. Both variables are of float type, but in C, the square root function sqrt with no f suffix is a double precision function. In hardware, a square root function will be implemented, but this code implies a conversion from float to double, which is the input type of the function, and a conversion from the double precision type output by the function back to the float type of the variable. This can result in some very unnecessary hardware. If Vivado HLS was to automatically optimize this, it would result in differences between the C and the RTL, which are very difficult to control and analyze. These examples are among the many not so obvious challenges you need to be aware of when performing floating point design and are described in the application note. For anyone interested in floating point design, the application note is highly recommended. Just search for XAPP599 on Xilinx.com. This completes this video on floating point design with Vivado HLS, and thank you for your time.